Welcome to Software Engineering in the AI Era, where we explore recent advances in software engineering research. Today's episode synthesizes 11 papers published on April 26, 2025, examining the intersection of traditional software engineering practices and emerging AI technologies. We'll delve into the challenges, opportunities, and methodologies that are reshaping how software is developed, tested, and maintained in an era of rapid technological change. These papers collectively highlight how artificial intelligence, particularly large language models, is transforming the software development landscape while introducing new considerations for practitioners and researchers alike. Let's begin with an overview of software engineering research and its significance. Software engineering, classified as SE on the ArXiv preprint server, involves the systematic application of engineering approaches to software development, operation, and maintenance. As software systems grow increasingly complex and become embedded in critical aspects of society, the need for robust engineering principles has never been more important. Current research reveals a fascinating tension between traditional software engineering practices and emerging AI-assisted approaches. In domains like healthcare, transportation, and financial systems, reliable software isn't just desirable, it's essential. Large language models are now transforming development processes, testing methodologies, and maintenance practices, creating both opportunities and challenges that researchers are actively exploring. The first major research theme emerging from these papers focuses on LLM integration in software development processes. Z and colleagues discovered that beginning programmers struggle significantly with LLM-generated code, achieving only a 32.5% comprehension rate. This raises important questions about the educational implications of AI coding assistance. Garusi and team revealed that ChatGPT error rates vary considerably across different development phases. Early phases like requirements gathering and design show relatively lower error rates, ranging from 5 to 20%. However, later phases including coding, testing, and maintenance exhibit much higher variability, with error rates between 10 and 50%. These findings highlight the tension between the productivity gains offered by LLMs and the comprehension challenges they introduce, suggesting that careful consideration is needed when integrating these tools into development workflows. The second research theme centers on software testing and quality assurance, with researchers adapting traditional methods for AI-assisted development. Azanza and colleagues presented a framework for continuous evaluation of LLM test generation in industry settings. This approach addresses the challenge of rapidly evolving AI capabilities and their impact on test reliability. Richarik and team introduced MMT4NL, a novel framework for evaluating trustworthiness in LLMs when used for in-context learning scenarios. These papers demonstrate how traditional testing principles are being extended and modified to address AI-specific challenges. There's a particular focus on developing reliable metrics for evaluating AI-generated tests, as industry adoption of these technologies requires robust evaluation frameworks that can provide confidence in automated testing approaches. The research suggests that while AI can enhance testing processes, specialized techniques are needed to ensure quality. The third research theme explores bug detection and reporting through AI-enhanced approaches to software quality. Acharya and colleagues introduced Bugs Repo, a comprehensive dataset of bug reports from Mozilla projects that enables more systematic research in this area. Rahman and team achieved an impressive 98.5% F1 score in detecting leaked secrets like API keys and credentials in source code using fine-tuned LLMs. Their work demonstrates how hybrid approaches combining traditional techniques with AI can yield superior results. Particularly notable is the significant reduction in false positives compared to regex-only approaches that have historically plagued secret detection tools. These papers highlight how LLMs demonstrate a remarkable capability to understand the semantic context of potential bugs, moving beyond simple pattern matching to more sophisticated analysis that considers code semantics and developer intent. The fourth research theme encompasses scientific software sustainability and multimodal interfaces, representing emerging areas of focus in software engineering research. Thacker and colleagues made the surprising discovery that scientific software actually has a longer lifespan than non-scientific counterparts, contradicting common assumptions about scientific software abandonment. Ahmed and team explored inferring questions from programming screenshots, investigating how visual inputs could enhance developer AI interactions. Ostas and colleagues focused on automatically detecting code comment smells, problematic commenting practices that can hinder maintenance. These papers point to an evolution toward multimodal programming interfaces that go beyond text-based interactions, while also highlighting the unique characteristics of scientific software development that challenge conventional wisdom about software sustainability and maintenance practices. Several groundbreaking discoveries stand out across these papers. John and colleagues demonstrated that LLMs can dramatically improve microservice failure localization, reducing diagnostic time from minutes to seconds in complex distributed systems. Z's team found that beginning programmers struggle significantly with LLM-generated code, raising important questions about AI's role in programming education. Thacker and colleagues revealed that scientific software shows unexpected longevity compared to commercial counterparts, challenging established assumptions about scientific software sustainability. Raman's work showed that fine-tuned LLMs can substantially reduce false positives in security-critical tasks like secret detection, achieving near-perfect accuracy while allowing for secure local deployment. Finally, Gurouzi's comprehensive analysis demonstrated that ChatGPT reliability varies dramatically across development phases, with conceptual tasks showing more consistent performance than implementation-focused activities. Researchers employed several common methodological approaches across these papers. LLM fine-tuning was prevalent, with researchers like Raman, Zhang, and Acharya creating specialized models for specific software engineering tasks. Empirical user studies were conducted by teams like Z and Ahmed to evaluate how humans interact with AI systems in programming contexts. Dataset curation emerged as another important methodology, with researchers like Thacker and Acharya creating comprehensive benchmarks for reproducible research. Prompt engineering techniques were explored by Ahmed and Richarik to optimize interactions with large language models. Finally, hybrid approaches combining traditional software engineering techniques with AI capabilities showed particular promise in works by Raman and Zhang, leveraging the complementary strengths of different methodologies while mitigating their individual limitations. Let's examine the first seminal paper in detail. Z and colleagues investigated how beginning programmers understand LLM-generated code, conducting a rigorous study with 32 CS1 students across 160 task instances. Their findings revealed a concerning 32.5% success rate in understanding AI-generated code, identifying specific barriers including language difficulties for non-native English speakers, unfamiliarity with syntax patterns, and automation bias. The tendency to trust machine-generated output without critical evaluation. This research directly challenges the prevalent narrative that LLMs will democratize programming by making it accessible to beginners. The findings have significant implications for computer science education, suggesting a need for explicit instruction in reading, evaluating, and modifying AI-generated code. Without addressing these comprehension barriers, AI tools might inadvertently create new obstacles rather than opportunities for programming learners. The second seminal paper by Thacker and colleagues analyzed over 18,000 scientific software projects and contradicted widely held assumptions about scientific software abandonment. Their research demonstrated that scientific software actually has a longer lifespan than comparable non-scientific projects, providing empirical evidence that challenges conventional wisdom. The researchers identified key factors associated with software longevity, including a project's position in infrastructural layers of the software stack, the number of downstream dependencies it supports, mentions of publications related to the software, and government participation in development. This last factor proved particularly significant, as government involvement substantially increased project lifespan. These findings suggest that scientific software development may have inherent characteristics or practices that could benefit the broader software engineering community. The third seminal paper by Zhang and colleagues introduced ThinkFL, a system using self-refining LLMs for microservice failure localization. This innovation dramatically reduced failure diagnosis time from minutes to seconds in complex distributed systems while simultaneously outperforming state-of-the-art models in accuracy. The researchers demonstrated that reinforcement fine-tuning can equip even lightweight models with sophisticated reasoning capabilities, making deployment practical in real-world settings. This work addresses a critical challenge in modern distributed systems reliability, where traditional debugging approaches struggle with the complexity of microservice architectures comprising hundreds or thousands of interdependent components. The approach makes efficient failure localization feasible in production environments by reducing both computational costs and response times, potentially preventing costly outages and service degradations. Looking toward the future, several promising research directions emerge from these papers. There's growing interest in developing LLMs that can adapt their output complexity to match user expertise levels, potentially addressing the comprehension challenges identified by Xi and colleagues. Creating standardized evaluation frameworks for AI-assisted software engineering represents another important direction, building on the work of Azanza and Richarek. The exploration of multimodal interfaces for programming environments, as investigated by Ahmed, points toward more intuitive developer-AI interactions. Researchers are also investigating how to preserve code comprehension while leveraging AI productivity gains, addressing the fundamental tension identified across multiple papers. Finally, building hybrid systems that thoughtfully combine traditional software engineering practices with AI capabilities appears to be the most promising approach for realizing the benefits of AI while mitigating its limitations. In conclusion, AI tools are transforming software engineering, but they introduce new challenges in comprehension and education, as demonstrated by Xi and colleagues' work with beginning programmers. Hybrid approaches combining traditional techniques with AI show the most promise, as evidenced by the success of Raman's secret detection system and Zhang's microservice failure localization. The research collectively suggests that software engineering must balance productivity gains with quality, reliability, and human understanding. As these technologies continue to evolve, maintaining this balance will be crucial for developing software that meets the complex needs of modern society while remaining comprehensible and maintainable by human developers. This research synthesis was created using multiple AI tools working in concert. The content generation was performed using Anthropic's Claude 3.7 Sonnet model, while text-to-speech synthesis provided the audio narration you're hearing. Visual elements for the original presentation were created using Grok for image generation and data visualization. All generated content was reviewed by a human expert in software engineering research to ensure accuracy and relevance. This approach to research communication itself demonstrates the hybrid human-AI collaboration that many of the papers suggest is the optimal path forward for software engineering. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from ArXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.